Hello, we are going to talk about the differential equation of simple pendulum. Our team is composed by Stephanie, Paul, and Alberto.
The simple pendulum. The objective of our project is that our experiment focuses on the simple pendulum, and we want to prove a proposed formula for this movement on a vertical plane is correct through the measurement by sensors. The description. Any object that swings back and forth is a physical pendulum, but we will focus on only one type that consists in a root of length L fixed with a mass M at one end, the simple pendulum. When the vertical motion performed is described, the mass may be negligible and that there is no external force acting on the system. In that picture, we see that the angle of displacement is theta, and this is related to the arc S of a circle with a radius L, by S equals to L multiplied by theta, so that the angular acceleration is this one. From Newton's second law, we obtain that the force is equals to mass multiplied by acceleration. We substitute the equations of acceleration in this one. We also see that the tangential component of the force due to the weight W is sin of theta multiplied by the mass and the gravity. As the direction of this force, we have minus mass per gravity per sin of theta, because pointing to the left is theta higher than 0 and to the right is theta less than 0.
First, we can start with the formula of the Newton's second law to obtain the differential equation. We know net force that acts in our pendulum is equal to its mass times the acceleration. On the one hand, we can observe net force is equal to the component in x of the weight because the component in y is countered by the tension of our pendulum. We can substitute the net force with the value of that component. The value is mass times gravity, which is the weight, multiplied by sine of theta. On the other hand, we can take the value of displacement as the arc of the trajectory of our pendulum. We know arc is equal to the radius times the angle, and in this case the radius is equal to the length of our pendulum. Then we can remember that acceleration is the second derivative of the displacement. We change the derivative in terms of the arc and then in terms of the angle. In this part, L is a constant. Now we substitute the values of the force and acceleration with terms that were obtained. We can eliminate the mass of our formula because it's a common term. Then we pass gravity and sine of theta on the other side to equalize our formula to 0. After that, we can divide all the formula over L to obtain our differential equation. Now we have a nonlinear differential equation that we cannot solve it, although we can transform it in a linear differential equation. To linearize our equation, we can compare the values of theta in radians with sine of theta. We observe that values are roughly the same when we have little angles. We can generalize that theta and sine of theta are the same for angles lower than 30 degrees. Finally, we can substitute sine of theta by theta in our nonlinear equation to obtain a linear differential equation. Now, the equation that we are going to solve and analyze is the second derivative of theta plus gravity over length multiplied by theta equal to 0.
The data acquisition system that we're going to use in our project is the Arduino one with the sensor HC-CR04 ultrasonic distance sensor economic. This sensor is going to measure the distance below the pendulum to calculate the grades in radians. The list of the parts required, these are going to be the HC-SR04 ultrasonic distance sensor economic, the Arduino one weight, thread, a table of measures to check the grades of the pendulum, and a universal support to sustain the pendulum.